So, 3 sections left to get through. So we've seen the generating function, which is a couple generating functions, one for triple functions, one for the Dr. polynomials. Here we look at some examples of applications of the generating function for solving problems involving electrostatic potential. Okay, so this first example, I'm going to have a picture from a textbook of situation modeling. So here we have, we're still working in spherical coordinates. So here we have the z-axis strangely oriented horizontally again. So you can think of this as axis here is where the xy plane sits. And we have the angle of inclination, theta, according to the physics convention, whereas it's phi for mathematicians. So at this point, z equals a, so along the z-axis, so the Cartesian coordinates would be z, 0, 0. So we have a charge q that's placed at that point. And what we want to do is figure out the potential at some point out in three-dimensional space. So r is the distance from that point to the origin, but r1 is the distance from that point of evaluation to where a charge is placed. So all these symbols are going to be needed in this example. And come back to the picture if we need to. Oh, sorry. Okay. So 0, 0, a, so z equals a is where the charge is placed. Now, the potential at that point is given by this formula. So the amount of a charge over 4 pi epsilon naught. And I want to give a definition of epsilon naught, and they do not, but I believe that came up in the previous oh, okay. I find it interesting that epsilon naught is brought up again here, and here too it's not mentioned what it actually means. I'm just going to take a quick scroll through. It's somewhere, but the first section is all about electronic polynomials. Well, that's unfortunate. Sorry. looks like they block over. I feel like this is a lost cause. Okay. I will have to deal with that later. Meaning of paragraph epsilon naught. Okay. So the electrostatic potential given by this fraction times 1 over v distance from a point at which we're evaluating potential to the location of the charge. But what we can do is we can express R1 in terms of the coordinates of the 2 points involved, because R1 is the distance from here to here. We can express it using the law of cosines. Because if we go back to the picture, because this segment R1, we want the length of that, but this is opposite the angle theta that is one of the spherical coordinates of this point. So that's how we can use the law of cosines to get R1 from the length of this, which is R, and the length of this, which is A. So here's our law of cosines expression here. U minus in the denominator, which is why it's raised to the minus 1/2. Now, but this expression here is 1 over the square root of all this. That turns out to be equal to the generating function for Legendre polynomials by choosing the right values for x and t. So what we need to do is, so here's the potential written again. Except what I've done to go from the original expression to here is I've pulled out a 1 over r. And the reason why I've done that is so that way I can get one of these terms inside to be a 1. And this is to make it agree with the generating function. The generating function is this expression for minus 1/2 power also, but one of the terms has to be equal to 1. So in the case where A is less than R, so the charge is closer to the origin than the point at which we're evaluating the potential, we pull out an R in the denominator. So now I have this. But this right here, this is exactly, if I match this to this, we're evaluating a generating function for polynomials in the case where t is equal to a over r, and x is equal to cosine theta. Within a generating function, we write that as this infinite series involving Legendre polynomials evaluated at cosine theta. Now, in a case where a is greater than r, we do the similar, except we pull an a out in the denominator instead of instead of an R. So we still get a term equal to 1. And then where we saw A over R before, now we have R over A. So we get a generating function evaluated at R over A. So we get the same kind of series, except that the roles of R and A are reversed. The reason we do that, one way versus the other, is to make sure series can converge. Now, if this factor, or the Legendre polynomial, Pn of cosine theta, if that wasn't there, then what you have is just a geometric series. For geometric series to converge, whatever you're raising to the nth power has to be strictly less than 1 in magnitude. That's why we use A over R if R is greater and R over A is greater. Now I just said, pretend that the Pn of cosine theta isn't there. Now, when you put it back, keep in mind what was said previously about the Legendre polynomials. On the interval -1 to 1, Legendre polynomials have a absolute maximum of 1. Right, they go between -1 and 1 on the interval -1 to 1. That's where the extrema are. So you can actually show that this series converges by virtue of a comparison test comparing to a geometric series, because the terms of this series are bounded by the terms of a geometric series. So, for very weird situations, we have a way of obtaining the electrostatic potential. Although what's not covered here, unfortunately, is a case where R is equal to A. Unfortunately, in that case, neither one of these series will converge. Questions about what we've seen so far? Now, in this example, we had the charge placed at a convenient point, 0, 0, A. But what we've seen here, we can use this approach that's involved to get an expansion of 1 over the distance between any 2 points, R1 and R2. By making use of the generating function for Legendre polynomials. As long as these magnitudes, R2 and R1, are not equal, just as here we needed them to be not equal. So it didn't matter otherwise what the relationship was to them, as long as they're not equal, we can use one series or the other. So we're going to make the same assumption here that the magnitudes of the individual points are different. So if we assume that R2 is greater than R1, we can do that without loss of generality. Then I go ahead and express this using the law of cosines again, where theta is the angle between the position vectors R1 and R2. That's the law of cosines again. And based on the assumption that R2 is greater 1, like before, go ahead and pull that outside the square root. So now I have a 1 here. And that allows me to express this in terms of a generating function for Legendre polynomials, with arguments with cosine theta playing the role of x, and R1 over R2 playing the role of t. And then we use generating function, this is what we get, do this infinite series involving R1 over R2 to the n, Legendre polynomials evaluated at cosine theta. If R1 was the greater, all I have to do is just switch R1 and R2 throughout. And the reason why this can be helpful is, especially if, for instance, if R1 is much smaller than R2, then in terms of the series would decay to zero rapidly in that case. So I can approximate the one over this distance with, like, for instance, taking the first few terms of the series and using the lowest degree Legendre polynomials. So another way of expressing this, covering all the bases, so as long as R1 and R2 are not equal, if I define R sum greater than to be the maximum, and then R sum less than to be the minimum, so whichever one of these that is, we can write the expansion this way. Questions about the expansion of R1 minus R2. Now, let's look at a different situation. Now we have two charges. One place at 0, 0, A, the other at 0, 0, minus A. And they have, the charges are opposite, so Q here minus Q here. So that is referred to as electric dipole, the two charges. And we want to evaluate the electrostatic potential at some point, somewhere in free space. Again, the distance from that point to the origin is R, the distance to the first charge is R1 again, so same meaning as before. R2 is the distance to the other charge. So then, the potential is expressed by, we use the same formula as before, Q over 4 pi epsilon over R1, but then we subtract that same expression applied to the other charge. We have Q for this one and minus Q for this one. So really, you're adding all the charges together, they have to have opposite signs. Now, so what I do here is, again, express these using the law of cosines. So this is the same expression that we had before for a first charge, where I pull out the r's, now I have this. And we go back to the picture. So theta is the angle that we have here, through which we use the law of cosines to get R1 in terms of R and A. Now I want to do the same thing using the law of cosines to express this segment of length R2 in terms of this segment again, and also this segment here. Now this segment is also of length A, so it's the origin to the second charge. But we need this angle. But I'll never remember these terms, the basic angle terms. I believe the term is supplementary angles. Yeah, the supplementary and complementary. Complementary is like this angle. Like, yeah. So supplementary angle. So pi minus theta is this angle that I'm looking for here. That will enable me to use the law of cosines to get an expression for R2. That's what I do over here. So I fill in cosine of pi minus theta. But if I use a trig identity for a cosine of difference, I'd have cosine pi, cosine theta, plus sine pi, sine theta. That turns out to be equal to minus cosine theta. So it gives me a plus here. So these expressions now become identical, except for having a minus in this case and a plus in this one. Now, one of these could be expressed in terms of a generating function from polynomials, as before. X is cosine theta, and then t is equal to a over r first charge, and then minus a over r for second charge. Now I have these power series and plus or minus a over r, the coefficients being the Legendre polynomials evaluated at cosine theta. But now if I look at these term by term, if p and the cosine theta in both, so when n is even and the minus goes away, terms will cancel. So I end up with this series expansion in only odd powers of a over r and times the odd Legendre polynomials at cosine theta. And so then I have a factor of 2 that comes out here. Now, suppose I let A go to 0. So the charges are converging to the origin. But the as the charge is approaching the origin, the magnitude of the charge of Q growing in such a way that the product to QA remains constant. The constant is mu. So what that would mean is, so 2QA is, so that's the constant mu. But then I have, in the first term, I have r squared denominator. And then the other terms, as a goes to 0, but these other terms will go to 0. So in the limit as a goes to 0, I only am left with this first term. So the numerator here becomes mu, and everything else still down here. Although, whoops. Okay, something's off here when I have epsilon all the way through. Check that here. Oh, yeah, it should be epsilon naught throughout. Fix that. check and see if I missed anything else. Oh, I did. Okay. All right. Oh, oh. So that's one situation we can have. Another possibility is suppose we have a pair of dipoles of opposite orientations. And one with negative charge for both cases at the origin. And I have a picture for that. All right, so this situation, we have it's called a linear electric quadrupole. So I have Q and minus Q. And then I have, so the charge minus Q is to the left. So that's one dipole. And then I have another dipole. If I take the Q and minus Q and flip it around, so I have Q to the left, minus Q to the right. But then I have both negative ones sharing the same space with the origin. Then this gives me a quadrupole. So I could try the same thing, same approach, to get an expression for the potential as A goes to 0. And what happens in that case, things cancel a bit differently. And this term, so r to the minus 3, P2 cosine theta times a constant factor is what I would get. More generally, if we have several charges placed at different positions, but still along the polar axis, so the z-axis, then this is what we get in general. So we have the sum of the charges is the first term in square brackets, and then notice the charges multiplied by AI. So we have a first degree Legendre polynomial. Keep in mind the 0 degree Legendre polynomial is just 1. So all the terms have the same form. So sum of qi times ai to a power. Whatever power we have that Legendre polynomial, that cosine theta, divided by r to that same power. So as long as r, that's the magnitude of a point in which we're evaluating the potential, as long as r is greater than ai for all ai. So in other words, if you think of all the charges that sit within, they're all along the polar axis, but you think of them as also sitting within a sphere, as long as the point r is outside that sphere, then this series will converge. Because you need to have this expression that you're raising to the nth power, a over r, has to be less than 1. These expressions that are multiplying Legendre polynomials, so sum of q times power a over power r, those are called multipole moments. So in other words, what you have in square brackets here is infinite sum of multipole moments times Legendre polynomials of cosine theta. I should mention that suppose you have a situation of charged particles, like a large number of them, and you want to evaluate the electrostatic potential that stems from how many charged particles you have. So you see the expansion here. There could be a lot of work to evaluate this. However, there's an algorithm that's called the fast multipole method that, at least approximately, computes electrostatic potential very efficiently. And it does this by regarding certain particles, like I say, if you are far away from certain particles, like where you're evaluating the potential, you get a good approximation by regarding those several particles as just one, where you add all the charges together. So, and the reason why I mentioned the fast multipole method is because in year 2000, it was named as one of the top 10 algorithms of the 20th century scientific computing. It's really quite a brilliant piece of work to evaluate potential so efficiently that whereas normally it'd be a whole lot of work, computationally speaking. Okay. Now, here we're using multipole expansion for electrostatic potential, but any other context where you have a inverse square force, like for instance gravitational attraction, this kind of expansion can be useful. Now, in the plenty of time that we have, are there any questions about this or about home?
I had something last Tuesday, so.
Okay. All right. So you're covered for now. So okay. Okay. Well, next week will all be all about 15.4, and then as a reminder, you do not have class Tuesday before Thanksgiving. So the Tuesday after Thanksgiving is going to cover the final section. That'll be done.
Yeah, did yourself that this time.
What?
Yeah, did yourself this time.
Oh,
This
how far?
time.
Oh, oh well.